So last time we just started to look at what's called the dichotomous search of a line section, and very helpfully the method is in the name here. You construct the bisector kind of in the middle of your domain, and you look either side, you're in a dichotomy, to decide which section to select for the next root finding. It has correspondence with bisection method, which is quite helpful for learning. Now today I'm just going to show a sort of handwritten example of doing the dichotomous search, and also a code example so we can see it all in action. Okay, hello again. So we're carrying on with this dichotomous search method for finding the minimum of functions. Remember, we start with a bracket AI BI, we construct the bisector, we look either side, epsilon either side of the bisector, and then select either the left or the right bracket. So I want to do a couple of things now. I first want to show you an example that you can do by hand. It's the example in the lecture notes. And then I want to show you how this method looks when it's in a MATLAB code. In the past, we've sometimes done this as part of the practical, but this year we've decided to just do a 2D optimization for the practical bit. So I'll cover this now in the lecture notes, lecture videos rather. So let's have a look at sort of worked example. Method. So we want to minimize f of x equals e to the minus x plus x squared. So something that's not necessarily easy to do by calculus, or not immediately obvious. And what we're going to do with, we're going to start with interval 0, 1. Okay, we kind of have a inkling about where the minimum might be, so we've constructed our initial bracket such that it's bigger than where that would be. And there's a way of checking that. It's just by evaluating functions within that domain. So let's just check that minimum, at least one minimum, is within this domain. Basically, we're going to evaluate f at the endpoints 0, 1, and then f at the midpoints. And if the function is less than the values at both endpoints, then there will be a minimum. So it turns out f0 is 1, f1 is 1.3679, 4 decimal places, and f at 0.5 is 0.8565. So f of 0 is greater than f of 0.5, and f of 1 is also greater than f of 0.5. So is minimum domain of interest. It's like quite a bit analogous to the intermediate value theorem for finding roots, where you look at the opposite sign of the function at either side of the domain. Here we're looking for the minimum, so we look at just 3 function values. Okay, so that's showing that the minimum does kind of exist within this interval. Now let's apply. We haven't really used the dichotomous method. basically we need to choose an epsilon, right, either side, and we need to choose it that it's much smaller than the domain. So it's still finite, but it's significantly smaller than 1. Okay. Take it to be 10 to the minus 3. Okay, and then we construct the bisector. Okay, so we use it to say C0 equals A0 plus B0 over 2, which is simply 0 plus 1 over 2, which is a half. Okay, so that's this. And now we're going to look either side of C0. So we have f as C0 minus epsilon and f as C0 plus epsilon. And remember, if it's less, whichever of these is less, helps us choose whether to use the left or right brackets. So f of C0 minus epsilon is essentially f 0.49, which is 0.8527, and f C0 plus epsilon is f of 0.51, which equals 0.862. So the C0 minus epsilon is less, yep, f of C0 plus epsilon implies select left brackets. So what we've done graphically here, working down now, so up, so we start off with 0, 1, we had 0.5, we looked at either side, epsilon either side, and we've selected the left bracket, so the new bracket is 0.51 to 0, and we look again, that's now A1, that's B1. So if we now do our bisector C1, so C1 is 0.51 over 2, yeah, bisector, which equals 0.255, and if we then carry on, I'm just going to do not do all this explicitly, just do yourself if you want. C1. So that's the new bracket, 0.8427, 0.834. So this time it's the other way around. The right bracket is so f C1 minus epsilon is greater than f C1 plus epsilon, implies select right bracket. Yeah. So what we've done graphically now, so we started off with we bisector, then we looked at epsilon either side. First time we selected the left bracket, then we constructed the bisector. I'm making a big deal with it there. We looked again epsilon either side, and we selected the right bracket. And each stage it's getting the interval is getting less, halving each time approximately, and we keep on iterating. And you'll find eventually that you can always verify that, you know, that the minimum has been found, because if the function at the bisector will decrease. Okay, so that's how it works in a sort of by hand example, but of course really where you want to use it is in code. So let's have a look at some code. I'll post up as well. So this is something I'll post up on LE. And post up the codes that I use each time. This code dicot.m. Let's just see the preamble before we jump straight into the code. So I'll just set the format to long format for this case. Let me scribble over it. Follow my own advice. This is his number of iterations. Actually, let's make my pen a little bit thinner. And then A and B is my initial interval or bracket. And then we've got some tolerances, but this is a tolerance, or the amount you want to converge the root by. And notice this time, rather than just setting epsilon, initially I've used a tolerance divided by 10 to set my epsilon value. So it's epsilon is small enough to satisfy the tolerance within which I want to reach the minimum. Okay. Defining my x variable, so x is in the interval from a to b by a small amount, this error. Then I have my function I want to minimize. Okay, so this is the function. What is 1D? This is a 1D function to minimize. And actually in the case of this example, I've got the function in a separate file. So this is just a passing. It's with your MATLAB, we use functions a lot. Sometimes we use them in line, where we use this at notation, and other times, and maybe more times, we use them as a separate file. So you just define a file with the same name as the function. And then the syntax is just like this. The output from the function is the name of the function times the with the input argument. And in this case, we just got a function which is absolute sine of x. So we're looking at this case. We're looking at the function y. Y equals absolute sine of x in the domain we're interested in. It's absolute value of sine. Okay. In fact, this function plots it up. Let's just do it. Okay, so this is a function we're interested in, a domain that we're looking at. So we're looking at the minimum at this point here. Okay. Actually, this is a minimum that can't be determined by derivatives, yeah? just jump to the end, we've the value we're looking at of sine of x modulus is pi. In this domain. Okay, so we're starting from this point, 1.2, I think it was, and we're looking at the minimum. So this is the minimum we're looking to zone in. I would say we couldn't determine that with calculus because the derivative is one of these absolute functions which has a derivative is undefined. So we're saying that's our minimum. Okay. So we know what the where the minimum should be. So it's a good way of testing the method. Then we have a loop basically where we either stop the loop when the error is less than the tolerance, so we keep the loop going whilst the error is greater than this tolerance, and the number of iterations is greater than the number of iterations we set. So we've set number of iterations here at 20, but of course if it reaches the minimum within the tolerance before then, this loop will still stop. So it's a sort of a double check really, but basically that's telling you to iterate until we think we've reached the solution. And then so the notation, as in all codes, is going to always be different from maybe what your theory is, but I've tried to annotate on the right side what it is. The first so you basically construct your 2 points x1, x2 are your 2 points either side of your bisector. So what we do, so that's your bisector, and we're going to construct x1 is one side, x2 is the other side. Yeah, so that corresponds to c1 minus epsilon and c1 plus epsilon, wherever you are. And then you evaluate the function u and v on those points, so at x1 and x2. Okay, so that's your function evaluation. Then we do the decision making bit, and all the decision making bit then is just an if statement. So if the function at x1 u, so you remember u is a function of evaluation on this side and v is a function of evaluation on that side. So if u is greater than v, then we select the right bracket. So that just means that your b value, so this is a and b are the right side, your a and b are your b is unchanged for selecting the right bracket, and your a is then set to x1. That's the first example. Then the second example is if you select the right bracket, means that b is set to x2. That's very efficient. And then you define the error as you it's basically the width of your bisector is derived of the error in your method, i.e. if you had a 0 bisector, if it was very, very small, then it would be a very small x. You increase the number of iterations, this is iterations, and then it basically displays 4 things: your iteration number, your a, your left bracket b, and your error. Okay, and let's see what the output looks like. So let's just expand up there. So the initial evaluation is a is 1, b is 2.64 in this case. Sorry, first time it's iteration 1. That's telling us the first iteration. A is 2.64, b is 4.1. The error is here. And then if you go down to say the 10th iteration, we're now going A and B a lot closer together. In fact, they're only differing by the second decimal point here. So this method is converging, and look, it looks very much like pi to me, doesn't it? So it shows that things are iteration, and then you can you get by the 14th iteration that actually it's by like the 4th decimal place that things A and B differ. So it's zoning in. If you evaluate your function f, we know the minimum is at 0 in this case, so that's actually helpful. It's very close to 0 at A, and very close to 0 at B. So the two things are converged. So so hopefully those are two angles that give you a feel for how these methods work. I'll stop there, and we'll do a little bit of a brief analysis of how fast dichotomous search converges, and that will motivate looking at something to do that improves on the speed, which is the golden section search. Okay, see you next time.